What's up, mathematicians? Welcome back to our lesson on the angle sum of a polygon. So in the last video, I asked you to work out a method to find the angle sum of any given polygon. In this video, I'll go over two approaches that you could use to find the formula for the angle sum of a polygon. First of all, if you found the angle sum of a pentagon and a hexagon, you probably noticed the following pattern. Let's go to the dot cam here. So consider that the angle sum of a triangle is 180 degrees, and then angle sum of a tetragon, remember what a tetragon is 360 degrees. Angle sum of a pentagon, if you figured it out, you would know that it's 540 degrees. And finally, the angle sum of a hexagon is 720 degrees. So what's the pattern here? Well, if you look at how much you would add to this number to get the next one, in each case, you would see that the difference is 180 degrees. 180 plus 180 is 360. 360 plus 180 is 540. 540 plus 180 is 720. And so what about the next polygon down? Let's say a sevengon. A sevengon is also called a heptagon. And I don't feel like drawing it right now, so I'm just going to write sevengon. Well, what is 180 plus 720? That is 900 degrees. So now we haven't proven it, right? But if this pattern continues, we would expect that a sevengon would have an angle sum of 900 degrees. Okay, so now let's try and find a formula and see if it corresponds with this pattern. See if it gives us the angle sum, see if it indicates that the angle sum of a sevengon, a heptagon, is in fact 900 degrees. So I've drawn here two heptagons, two sevengons, and I'll show you two methods that, the two methods that I typically see students come up with when they face this challenge. So the first method, the most common method that I see students come up with is this. They say, okay, let's pick a point, for example, this top point here, and let's go ahead and draw lines from this point down to the other vertices. So it's already connected to this one, so let's go ahead and draw a line from this vertex down to this one. Let's go ahead and draw another line from here down to here. Then let's draw a line to this vertex here and another line to this vertex right over here. Okay, and of course we don't draw a line there because that one's already there. Now we notice that, wait a second, I have a bunch of triangles. How many triangles do I have? Well, I have 1, 2, 3, 4, 5 triangles. Okay, and each of these triangles has an angle sum of 180 degrees, and all the angles of all the triangles end up overlapping with being the same as the angles of the original polygon, the heptagon. How many triangles are there? We can easily count 1, 2, 3, 4, 5. But imagine if we're going to use this method for any number of triangles. Well, there are a couple different ways to think about it, but one is this. From the perspective of this point, which is a vertex of all the triangles, how many triangles are there? Well, each triangle is made, or has, you could say, a base, has the opposite side as one of the sides of the original polygon, with two not being used, right? We don't use this one and we don't use this one. So you skip the two sides that are actually connected to the point that you made all the lines from. But all the other sides are sides of unique triangles. So what does that tell us? Well, it tells us that somewhere in this formula we might have an n minus 2, where n is the number of sides in the polygon. The reason we subtract 2 is because we skip these two sides that the this vertex is already attached to. So we want all these other sides, which are sides of unique triangles, different triangles. Well, we also know that the angle sum of all these triangles is 180 degrees. So we can multiply 180 times n minus 2. Okay, well, if we do that, that should give us the angle sum of all these triangles combined. So let's see what happens if we do that for the 7-gon. Well, that would be 180 times, well, 7-gon has 7 sides, minus 2, which equals 180 times 5, which does in fact equal 900, which is what we expected to get from the pattern, right? Now that doesn't mean we've proven it, but it's always a good sign when things are working out the way that you expect them to work out. Okay, so now let's look at a second method. I have had some students come up with this method, but it's definitely less common for students to come up with this second method. And the other method is, instead of drawing lines from one of the vertices, is pick a point somewhere inside the polygon. You could try to find it in the middle, but it doesn't have to be the middle. I would recommend doing it more or less close to the middle, whatever the middle is. And now we're going to draw lines from this center point to each vertex of the polygon. Okay, I'm going to go ahead and draw 7 lines here. 1 to each vertex of the polygon. And you should go ahead and follow along. If you haven't done this method, you should go ahead and do this in your notes as I'm doing it. Of course, you can always pause the video if you need a little extra time, if I'm getting ahead of you. Okay, so now we have, again, the polygon sliced up into several different triangles, right? A number of different triangles. And how many triangles are there? Well, each triangle has this interior point as a vertex and has a different side of the original polygon as an opposite side from this vertex. So what that means is I actually have 7 triangles, the same as the number of sides from the original polygon. Okay, well, I know that the angle sum of each of these 7 triangles is once again 180 degrees. So I can say, okay, I'm going to say 180 times n. That will give me the angle sum of all 7 triangles. However, that is actually too much, because see all these angles here that meet at this point right here? Well, all those angles, I mean, let's think about it. All those angles combine to be one complete circle, right? Which is 360 degrees. Interesting. And, well, see, the issue is all these angles here, they're not part of the angles of the original polygon, so we want to exclude them. So how much, like what magnitude of angle measure are we excluding? Well, we're excluding 360 degrees. So we can say, okay, 180 times n minus 360. So exclude all these angles meeting at this center point. So here we have 2 different formulas, right? I don't know, what color should I use? I don't know. I'm trying to pick a color that is provide some contrast to both of these. So anyway, I have one formula over here, and I have another formula over here. Okay, and this looks like I have 2 different formulas for the same thing. But if you remember your algebra, you might realize that, wait a second, these 2 formulas are actually the same formula. Because what happens if I take this formula here, 180 times n minus 2, and I apply the distributive property. I say, okay, let's distribute the 180 times the n. and the 180 times the -2. Well, then I'm going to get that I'm going to get 180n minus 360 degrees, which is this formula right here. And of course, if I were to plug 7 in for n, I would once again get 900 degrees, and so it fits the pattern, okay? And so what is the angle sum of a polygon? Well, it's 180 times n minus 2 or 180n minus 360. Either of these formulas will work because it turns out they're actually the same formula. Okay, so what about a proof? I mean, that would help us feel better about these formulas and the fact that this pattern will in fact continue. So let's talk about how we might write a proof for this. And I'm actually going to start this on a new page. Oh, well, look at that. Looks like I'm all done with this notebook. I'm going to start another notebook. Okay, so here I am in my brand new notebook, first page, and let's look at the proof. Okay, so I'm going to once again draw a diagram here. This particular one has 7 sides, but I want to consider a polygon with any number of sides. So for my given, I'm going to say given a polygon, and I'm going to call it A, B, C, dot, dot, dot. So it's going to have at least 3 sides, right? Because every polygon has at least 3 sides. So it'll have at least A, B, C. And then the letters might just go on and on. There'll be as many letters as there are vertices to correspond with the letters. And so in this particular one, I have A, B, C, D, E, F, and G. Okay. And now my goal is to show that the angle sum of ABC dot 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 is 180 times n minus 360, where n is the number of sides, okay, of the polygon ABC dot dot dot. Okay, so there we go. I got my given, I got my goal. And I recommend that you write out this proof in your notes as I go through it. I'm going to take the time to actually write it out. It'll take a little while, but go ahead and write it out in your notes as we're going along. So step number 1, I'm going to go ahead and just say draw the point P inside or in the interior of, actually, if I just write inside, interior of, but if I just write inside, I should say inside the polygon ABC dot dot dot. Okay, now thinking about our axiomatic system, how do we justify that we can draw a point P inside the polygon? Well, that of course is rule number 1. I'm going to abbreviate as R1. Says I can put a point anywhere. So I'll go ahead and just do it here with my marker, make it pretty. So I'm going to call it P, point P. Okay, and then step 2, we're going to go ahead and draw lines from P to each vertex, okay? And so from P to E, P to F, P to G, P to A, P to B, P to C, and P to D. Okay, I'm drawing freehand, I know, which means my drawing is not quite as pretty, but it's a little quicker than using the straight edge. Although I always recommend use the straight edge. But for the sake of time, I'll draw freehand. Oh yeah, and so what is our justification? based on our axiomatic system for this? Well, of course, we know that rule number 2 says we can draw a point or draw a line from any point to any other point. So 2 points will determine a line. And so this is rule number 2. Okay, what next? Well, we just need to recognize that what we have here, right? So I'll put this. So note that ABC ... So our polygon has been divided into n triangles. Now remember, n is the number of sides of the polygon that we're working with. Okay, so it's been divided into n triangles with a side of the polygon as one side of each triangle. Okay, so it's been divided into n triangles. Now, what is our justification for this? I mean, if the skeptic is like, wait a second, how do I know that it's been divided into n triangles? I mean, you could say, you know, it's obvious, right? Like just look at the diagram. You know, it's sort of it's sort of up for interpretation, right? So I'll say I'll just write obvious from diagram. Okay, but maybe you are up against a really picky skeptic who's like, wait a second, how do I know it's so obvious from the diagram? And so, you know, there is some potential for questioning a bit further here. And as a result, maybe this isn't a completely rigorous proof. And, you know, we can talk more about what that means later. But for now, we're just going to say, based on the diagram I have, it seems clear. Okay. All right, so step 4. Well, the angle sum of all the triangles is 180 times n, right? So angle sum of all the triangles is 180 degrees times n. And what is our justification for this? Of course, it is the triangle angle sum theorem. I'm going to abbreviate this as TAS, triangle angle sum. So that seems pretty clear. So I have n triangles, and therefore the angle sum of all the triangles is 180 times n because of the angle sum of a triangle theorem. Okay, so all these angles of the triangles, all the angles of the triangles are part of, basically are part of the angles of A, B, C, ... except those meeting at P. Okay, so if we look at the diagram, we see all the angles of the triangles, right? And all of these angles out here, those are all angles that are part of the original polygon, A, B, C, etc. But then all these angles here that meet at P, those are not part of the angles of the original polygon. So that's why I say except those meeting at P. Okay, what is our justification here? Again, I guess obvious from the diagram. Okay, and so, you know, up for, you know, possibly some debate here, but it seems clear based on the diagram. Okay, so let's say step 6. So the angles meeting at the point P make a full circle. So the angles meeting at P, I'll say make a full turn. Make a full turn. Oops, you can't even see what I'm writing there. I'm off the screen. So the angles meeting at P, make a full turn and add up to 360 degrees. I'll let you think about what we could say to justify that. We could go back to the definition of angle and work with that, but I'll go ahead and let you think about that one. And let's go ahead and go to step 7, which will be our last step. So therefore, the angle sum of ABC ... is 180 times n minus 360. Okay? Or I may put 180 degrees times n minus 360 degrees. Okay, which is the thing we were trying to prove. So we're done. Now, once again, the justifications might seem a little bit unclear, and that's just the nature of what's going on in terms of we're moving into some different territory here than what we've been focusing on in the past 2 units. And actually, this proof probably feels a little bit different to you than most of the proofs that we did in the previous 2 units. And I'm actually curious how you feel about it. I mean, this proof, to me, it actually feels a little bit more narrative. It seems a little awkward almost to write it with these steps. I feel like maybe a paragraph or just a verbal explanation, which is, one way, like the Greeks had this conception of a proof as sort of an explanation. Maybe a verbal explanation or a paragraph would be better suited to convincing a skeptic of this logical flow and this result that the angle sum of a polygon is 180 times n minus 360. Okay, but I am curious how you feel about this proof versus the proofs that we did in the previous 2 units, okay? What do you prefer? Do you prefer this proof, which maybe feels a bit more narrative? Do you prefer those other proofs which fit more neatly in the columns with the steps and the justifications? Let me know in the comments. Give me a comment. Let me know which proof do you actually prefer, okay? And so that's actually going to wrap up this particular lesson. However, don't forget to practice, right? If you want to get better at math, you have to practice, okay? So on the website and also linked down in the description, I will have a document with practice problems for this unit. So do the practice problems for lesson number 1. And yeah, that's it. That's the end of this lesson. In the next lesson, we will look at how different polygons can be used to tile the plane. We'll see you then.